For some people, lasers conjure up an image of dangerous weaponry on a grand Star Wars scale. A few of them become so frightened of laser radiation that they neglect more familiar hazards, like high-voltage electricity, which may be much more dangerous than the laser they're using. It's true that nearly all lasers can be hazardous, especially to the eye, but there are very different levels of risk connected with different types of laser, and the risks are related to how you use the laser and to your skill, training, and even state of health. The purpose of this program is to point out the potential hazards that you're likely to encounter when you use lasers in research and teaching laboratories. We're going to show you ways of reducing those hazards so that you can protect yourself and others from possible harm when you're starting out on laser work. It's very important to understand the difference between white light, as we receive it on the Earth from a light bulb or the sun, and the radiation produced by a laser. Unlike conventional light, laser radiation is unique in that it is monochromatic, coherent, it's frequently plane polarized, and its divergence is very small. The sun is so bright that it's dangerous to look at it. But if you were to do so, its parallel white light would form an image on your retina. This image would be a disc around 100 microns in diameter. Laser radiation normally travels as a very narrow beam with extremely small divergence, sometimes as little as 0.1 of a milliradian. This laser beam hardly diverges at all along the whole length of this corridor. Because of the unique properties of laser radiation, your eye can focus a beam of laser light to a minute point, increasing the power density by around 200,000 times. Compared with a conventional light source of the same intensity, a laser will produce the smallest image size, around 20 microns. So the laser is unique as a source of radiation which can be concentrated on a particular point. When we add that to the way the human eye works, we have a potentially disastrous combination.
Can you smile, please? That's lovely. Fine.
Blinking, the eye's first natural defense system to very bright light, takes about 1/10 of a second to happen. But many lasers can do irreparable damage before this blink response can provide any protection. This one concentrates all its energy into less than 1/millionth of a second.
3, 2, 1. Bingo.
When we perform a task that requires visual concentration, our eyes are moving all the time. Because, unlike a video camera, which can resolve detail equally well throughout its field of view, our eyes can only resolve fine detail at one point of the visual field. This is the fovea. It's the part of the retina with the greatest concentration of cones, colour-sensitive photoreceptors, and it's only about 200 microns in diameter. If you were to look straight along the axis of a laser beam, it would be directed onto your fovea, and this most crucial part of your eye would be damaged. Now, if the central part of a video camera tube is destroyed, there's still a considerable area left that can provide useful information. But if your fovea was damaged, you'd only be left with peripheral vision in that eye, so you'd lose a great deal of detailed vision. This type of damage does not heal. If it happened to you, you'd probably have to be registered as blind in that eye. And if it happened to both your eyes, you wouldn't be able to read at all. All parts of your eye are at risk from laser radiation. Different parts absorb different wavelengths. Naturally, it's the radiation that is absorbed which does the damage. As we've seen, visible radiation is absorbed by the retina, so that's where you'd be injured by visible laser light. But there's a very real risk too with invisible laser radiation. The cornea absorbs in the far ultraviolet. So at this wavelength, your cornea is at risk, as well as your conjunctiva and eyelids. Near ultraviolet radiation goes through the cornea and aqueous humour and is mainly absorbed in the lens. Near infrared radiation is an extra hazard. You can't see it, but it goes through your lens, so it'll be focused to a tiny spot on your retina where it can cause damage without making you blink or look away. Far infrared radiation doesn't get beyond the cornea, and so again, it's the cornea and eyelids that are at risk. At the boundaries between visible and invisible radiation, the eye sensitivity falls off. So what may look to you like a very feeble red glow could in fact be the beam from a powerful laser emitting at around 715 nanometers. If a powerful laser beam does hit your retina, it'll cause damage. The type of damage depends on the type of laser. When radiation from continuous wave and long-pulsed lasers hits your retina, the cells absorb the energy over a relatively long time period. The damage is caused by the thermal and photochemical effects of the radiation. It's with this type of cell damage that you aren't necessarily aware that you've been injured. A short pulsed laser may deliver the same amount of energy as a continuous wave one, but over a much shorter time. The cells are suddenly heated to boiling point and explode, causing mechanical damage and shock waves which injure a wide area of the retina. If the damage is severe enough, you'll lose all your sight in that eye. These hazards are made worse if the laser laboratory is fairly dark, as your pupils are likely to be dilated. And that increases the chances of laser radiation entering your eye. So far, we've concentrated on the risks you run of damaging your eyes through carelessness in the laser lab. Although eyes are most at risk, other parts of the body can also be severely burned by excess exposure to laser radiation. Short-pulsed, high-intensity ultraviolet lasers need extra care, as exposure to this radiation may cause the risk of skin cancer. Now, before we put you off using lasers for life, are there safe levels of laser radiation? The international standards divide lasers into classes, depending on specified accessible emission limits. That's the amount of radiation that people can get access to in normal use, also known as AELs. The definitions are very precise, and you should refer to the standards if there's any uncertainty over which class the laser you're using belongs in. But to put it simply, Class 1 lasers are those that are inherently safe, either because of their very low output or because their engineering design means that the very lowest AELs can't be exceeded. This ruby laser, with an energy of several joules, is totally enclosed, and no laser radiation can escape into the environment. So it's in Class 1. And this barcode reader emits so little accessible radiation that it too is in Class 1. Class 2 lasers are low-power devices, emitting only visible radiation. Your blink reflex protects you against the accidental viewing of this radiation. This 0.95 milliwatt continuous wave helium neon laser is such a Class 2 device. So long as you don't stare into its beam, there shouldn't be any risk of injury from a Class 2 laser. Class 3A lasers are more powerful devices, still emitting only visible radiation. They can cause injury if you stare into the beams or observe them with optical instruments. With Class 3B lasers, any exposure of the eyes to the beam is risky, not just staring at it. Class 3B lasers may also emit specified levels of invisible ultraviolet and infrared radiation. This helium-neon laser is one such Class 3B laser. In fact, you'll probably find more Class 3B devices in research establishments than any other types, as there are so many helium-neon lasers around. Finally, there are Class 4 lasers. These are high-powered devices, so powerful that even diffuse reflections of the laser beam, reflections off unpolished surfaces, may damage your eyes and your skin. The direct beam itself and spectral reflections off polished surfaces will almost certainly harm your skin. It'll definitely damage your eyes and can even cause fire. So how, without becoming paranoid, do you ensure that you can carry out your laser work in safety? Well, there are 3 lines of defence. First, there are engineering controls. The most obvious measure here is total enclosure of the beam. This is what's done with some very high-energy lasers to bring them into Class 1. When it is done, the conduits and beam covers must be interlocked with the laser power supply or a device that will intercept the laser beam at source. Even if you're not trying to get it into Class 1, you should aim to enclose a high-energy laser beam inside covers as far as you can. The beam of this cutting laser is enclosed all the way round until it reaches the cutting head. A polycarbonate screen gives extra protection against the radiation. The covers should be interlocked with the power supply. It isn't always possible to enclose the entire length of the beam because you may need to adjust prisms and so forth. But you can do a lot by running a laser beam inside conduits like this for as much of its length as possible. Enclosed or not, Class 3B and Class 4 lasers should only be used in laser-designated areas, which are restricted to authorized people who are trained and who've been suitably screened. Where it can be arranged, you should have each laser installation inside its own protective enclosure, which prevents anyone being exposed to dangerous levels of laser radiation. There are maximum permitted exposure levels laid down in the safety regulations. There should be warning lights over the outer doors of the laser-designated area and notices like these. If there are parts of the beam that can't be enclosed, then you have to take proper precautions to prevent people being exposed to excessive levels of laser radiation. You can put safety screens around each experiment to contain the laser radiation still further within the restricted area. If you're using an open beam Class 3B or 4 laser, there should be a fail-safe interlock to interrupt the beam if the lab door is opened. Like this. Spectral reflections are caused whenever a laser beam hits a polished surface. If you're using a prism to control a laser beam, there'll be reflections from its different surfaces. These reflections are almost as powerful as the main beam. If you rotate a prism or mirror, the reflections, of course, rotate twice as much. A very small movement of a mirror or prism can cause an unexpectedly large movement of the reflected beam. So, before you run the laser at full power, you need to check the direction of the primary beam and intercept any surface reflections, running at greatly reduced power. In some cases, you can use neutral density filters to reduce the output to safe levels for checking reflections. In this installation, they're mounted on a motorized disc. To reduce the risk of somebody accidentally moving a prism, and so causing large and unexpected movements of the reflected beams, you should enclose each prism, allowing small holes for the incident and emerging beams. Aligning pulsed lasers and those which emit invisible radiation is a problem. You can set up a low-powered visible laser to be coaxial with the pulsed laser and use that for your alignment checks. You need to make sure that the main beam and the reflected beams are going where you intend them to. Because your eyes are so insensitive to some wavelengths of radiation that can damage them, you should use a power meter to measure beam intensity rather than rely on what you think you can see. Each laser, and especially those in class 3A, 3B and 4, must be firmly mounted on a proper optical bench. The primary beam should be terminated within the limits of this optical bench. It must never be allowed to cross the floor space. The beam stop must be properly constructed and able to stand up to continuous use without being affected by the beam. It must also produce minimum scattered radiation. Naturally, laser beams should be arranged so that they point away from doors. You need to mount all optical components within the experimental area on properly constructed mounts, not plasticine. Optical fibres need to be terminated with proper fittings, not simply wedged in position or allowed to hang free. Where you're doing experiments with open beam lasers, try to arrange them so that the beams are all on a single plane, well below eye level. So those are the main engineering controls. And the second line of defence against laser hazards is administrative controls.
It should come about here. Charging.
When you're firing off high-energy pulsed lasers, you should follow a proper countdown procedure.
Charged. 3, 2, 1.
When you're not using it, you must protect each class 3B or 4 laser from unauthorised use by switching it off, removing the key of the safety switch and returning it to the authorised key holder. Despite all these precautions, there'll always be some experiments where you need to work close to hazardous levels of laser radiation. On these occasions, you have to take special steps to protect your eyes and skin, and personal protection is the third line of defence. No single type of eyewear will protect you against all laser radiation, but whichever goggles you wear, they should be approved under the Protection of Eyes regulations. They must be ones that cut out the specific wavelength you're using, and they need to have sufficient optical density at that wavelength to protect you against the maximum power of laser that you'll be exposing yourself to. A green filter is ineffective against radiation from an argon laser because its optical density at this wavelength is very small. But an orange argon filter has an optical density of 14 at this wavelength and gives good protection. The goggles need to be clearly marked with the wavelength they're designed for, their optical density at that wavelength, and the power level that they'll protect you from. The power level needs to be chosen for the worst possible case you could encounter, goggles can shatter if they're exposed to high-energy, short-pulsed lasers. Tunable lasers are a special problem, as they can be adjusted through a range of wavelengths. Broadband anti-laser goggles are designed to protect you in these circumstances, but they need to be selected with great care. There are special risks with semiconductor lasers. They're very small and portable, like this one, so they're much harder to regulate. Many of them emit around the boundary between red and infrared, where the output doesn't look bright, even though it may be damaging your eyes. Because they're so small, and because their beam can look so feeble, there's a very real risk that people won't treat these lasers with enough caution. Some people think that they aren't very dangerous because the early ones produced fairly divergent beams. But the beams are of laser radiation and can easily be focused to a tiny point. Appropriate broadband anti-laser goggles will give protection against this type of laser. Naturally, whichever type of safety goggles you wear, you'll need to be able to see enough to move about safely, to operate controls, and see whatever warning lights are in use. In this experiment, the beams from two different lasers cross. We've used liquid nitrogen to make them show up. When we put an orange argon laser filter in front of the camera, the green beam is greatly attenuated, but the red beam is unaffected. Because laser safety goggles are so selective in the wavelengths they protect you from, it means you shouldn't have different open beam experiments running in the same laser area at once unless they're under the control of the same person. In experimental work, you often need to carry out precise beam alignments. Of course, safety goggles will prevent you from seeing the beam itself. But even with goggles, you can often detect the fluorescence where the laser strikes the target area and use this to align the beam. In some cases, you may need to do the setting up without safety goggles, and then you'll need to take special precautions, such as turning the power down to safe limits and introducing neutral density filters, so you can align the beam without risk to your eyesight. Alternatively, you can use indirect viewing methods, such as closed-circuit television. You can also position a piece of burn paper or Polaroid film at the target area and test fire the beam at that. But in this case, you do need safety goggles and gloves. If you have to work in close proximity to the exposed beam of a high-intensity laser, you should wear suitable gloves and cover your forearms. This is particularly important if the laser is running in the ultraviolet. There are extra risks when you're working with a high-powered laser, quite apart from the effect of the beam itself on the human body. There could be hot metal flying around from cutting or welding spatter. Many plastics and metals give off toxic fumes when they're heated. Certain ultraviolet lasers generate hazardous ozone from the oxygen in the air. Ozone can also be formed from discharge within high-voltage electronic components, or even from faulty electrostatic dust extractors. And the fuel gases of some chemical lasers are toxic. So, adequate ventilation is important. When you're preparing dye solutions, you often use considerable quantities of solvents, such as methanol. Most of these solvents are flammable, and many of the dyes are carcinogenic. Keep the volume of solvents you're using at any one time to a minimum. Do the preparation in a fume cupboard, and return Winchesters of flammable solvent to a fire-resistant cupboard or chest immediately after using them. You often need to use cryogenic coolants, such as liquid nitrogen or helium, in laser work. One of the risks here is of getting cryogenic burns. Also, the coolants can reduce the concentration of oxygen in the air by displacing it. If you're working in a poorly ventilated area, you could even end up being suffocated. Anyone who's using cryogenic liquids needs to be aware of how easily liquid nitrogen condenses oxygen from the air. The boiling point of nitrogen is 13 Celsius degrees lower than that of oxygen. This Dewar flask contains liquid nitrogen. After just a few minutes, a quantity of liquid oxygen has condensed from the air. The tap on the vessel is sealed. When the liquid oxygen boils off in a sealed system, there can be an explosive overpressure of oxygen. This was caused just by the overpressure of oxygen. If it had come into contact with a flammable substance, it would have caused a violent explosion. The design and decor of a laser lab can have quite an effect on optical safety. The lab should be well lit and the walls light-coloured. This helps to reduce the pupil size of people working there. To reduce laser reflections, the walls should have a matte finish. All polished and metallic surfaces, apart from optical ones, should be sprayed matte black if possible. There should be fire-resistant blinds covering any windows to prevent laser radiation escaping and striking passers-by, or reflecting back across the lab. And it's not a good idea to have desk space for extended periods of reading or writing in a laser laboratory. You also need to watch out for hazards linked with the plasma tubes and electronic flash tubes that are used with lasers. They give off considerable amounts of invisible ultraviolet radiation, which can damage the eyes and the skin. Laser power supplies, which operate at 5 kilovolts or more, may produce X-rays. But for most classes of laser, the greatest risks are those associated with high voltage electricity. Pulsed lasers use capacitor banks, which may be charged to thousands of volts. So you have to make very sure that the capacitors are earthed before you do any work that exposes live conductors. Some solid-state pulsed lasers contain large choke coils. Very high currents, several thousand amps, can flow through these circuits. High-powered, continuous wave lasers often have high-energy electronics in their power supplies. The starting pulses sent to the plasma tubes may be as high as 30,000 volts. Alongside this, most high-powered lasers use water for cooling the power supply and the laser head itself. This cooling water is generally at high pressure. Flexible hoses are often used, and it's quite common to have leaks where the hoses join onto the equipment. When such leaks occur near the very high voltages and currents that lasers require, you have the potential for some very nasty accidents. An extra hazard is caused by this, the trailing main socket that you use to power up the electrical appliances that you so often need in laser work. Many people simply place these sockets on the floor underneath the bench without thinking of the risk that they present if there was a flood, especially in a room that could be dark. This is probably the commonest serious hazard that exists in laser laboratories. All such distribution boards must be raised above floor level, preferably attached to the wall or the optical bench. Because while looking into a laser beam could cost you your sight, being electrocuted would cost you your life. So, there are very real risks associated with lasers, but there are also sensible measures for dealing with them. To avoid the possibility of accidents in the laser lab, everyone working there should be in a good psychological state of health and not suffering from fatigue. The physical health of people who are going to work with lasers is also important to their safety. Pulsed lasers may cause epileptics to have fits in the lab, which could be very hazardous. And if somebody has poor vision in one eye, they'll automatically use the good one. So if they have an accident, it'll be their good eye that gets damaged. The Committee of Vice-Chancellors and Principals booklet, Notes of Guidance for Lasers, gives details of the precautions you must take if you're going to work with lasers. You need to study the booklet as well as watch this programme. Anyone who's working with lasers has a legal responsibility to ensure their own safety and the safety of anyone else who might be injured as a result of their negligence. You may need to undergo some form of screening and training before you start working with lasers. And there may be other checks when you complete your period of work with lasers. If anyone has an eye injury, they should be rushed to the nearest hospital which can deal with it. You need to find out where that is now, rather than when there's an emergency. Any accident which involves a laser must be reported to your safety officer, and your laser safety officer if you've got one. The equipment involved must remain untouched pending an investigation, and no further work may be done on it. I don't want you to get the idea that lasers are so frightening that you'll vow never to go near them again. Yes, there are risks, but the precautions are simple and based on common sense and good practice. Class 1 lasers are totally safe. Class 2 are safe for accidental viewing. Class 3A are safe unless viewed with optical aids. Class 3B are hazardous to the eyes. Eye protection is needed. Even diffuse reflections from Class 4 lasers may be hazardous to the eyes. The direct beam and spectral reflections are hazardous to the eyes, and eye protection is needed. The direct beams and spectral reflections from a Class 4 laser are also hazardous to the skin. Skin protection is needed. Class 3B or 4 lasers should be fully enclosed if this is possible. Where this can't be done, as much as possible of the beam should be enclosed. You need to take special precautions, including using eye and skin protection, if you're using open beam lasers of this power. Use fail-safe interlocks on beam covers and doors. When you're using laser safety goggles, take particular care to choose ones that will protect you against the wavelength and power of the laser you're using. Mount lasers on properly designed optical benches with beam stops. Watch out for direct and reflected beams from Class 3B and 4 lasers. Remember that with Class 4, you even have to beware of diffuse reflections. Remember the toxic hazards you may find in the laser lab. There are special risks with cryogenic coolants. And the most lethal risks are those associated with high-voltage electricity, capacitor banks, choke coils, and especially the combination of training sockets and high-pressure cooling water. Lasers are immensely useful devices, which have all sorts of applications in science, engineering, medicine, and research in general. As we've seen, there are considerable risks connected with them, especially the most powerful ones. But so long as you follow the principles in this video and in the CVCP Notes of Guidance, treat the laser risks with respect and use your common sense, you'll be able to work safely.